Good morning students, welcome back to session 5 of vector spaces class. So in the last class you have studied what's meant by a dimension of the vector space. The dimension of the vector space is the number of elements present in any basis of the vector space V. Okay, dimension of the vector space is the number of elements, number of vectors or number of elements present in basis is called the number of vectors in any basis is called the dimension of the vector space V. Now, and also we have proved that if V is a finite dimensional vector space, if V is a finite dimensional vector space, then and if V1, V2, etc. Vr or any R number of linearly independent vectors in V, then these linearly independent vectors can be extended to form a basis of V. Thus, in a finite dimensional vector space, any linearly independent set can be extended to form a basis. And also, we have proved any two finite dimensional vector spaces over a field. So, if V and W are any two finite dimensional vector space over a field F, then V and W are isomorphic. V and W are isomorphic if and only if they have the same dimension. Okay, the vector spaces V and W are isomorphic defined over the same field are isomorphic if and only if they have the same dimension. And also we have taken one example which is the real valued solutions or the solutions of the differential equation d cube y by dx cube plus 6 into d square y by dx square plus 11 into dy by dx plus 6y is equal to 0. So this is the given differential equation, and we have shown that the solution of this given differential equation is itself a vector space, and we have find out the basis for that solution set also. Okay, and so we have shown that every n-dimensional vector space Vf is isomorphic to Fn for some n. Every vector space, every n-dimensional vector space Vf is isomorphic to Fn. This is true for any n. Okay, these are the few results that we have studied in the last class. Now let us take up today's lecture. In that we will find, say, the dimension of the quotient space. Here we are going to find the dimension of the quotient space. So suppose W is any I may name it by some theorem. Say if W is any subspace of a finite dimensional vector space V. W is any subspace of a finite dimensional vector space V, then we will show that dimension of W is also finite dimensional. Dimension of W is finite, or W is finite dimensional. W is finite dimensional, and dimension of W is always less than or equal to dimension of V. Dimension of W is less than or equal to dimension of V, and dimension of the quotient space, say V by W, is equal to dimension of V minus dimension of W. Dimension of the quotients V by W is equal to dimension of V minus dimension of W. Okay, for this let us take up one by one. Say now, say we will take the dimension of since we are taken to be V is finite dimensional, let the n be the dimension of V. Okay, then n is the dimension of V means n is the maximum number of linearly independent vectors in V. Okay, n is the maximum number of linearly independent vectors in V. Now W is a subspace of V means W is a subset of V. So therefore n is the maximum number of linearly independent vectors in W also. Okay, since n is the maximum number of linearly independent vectors in V, n is also the maximum number of linearly independent vectors in W. Maximum is n. Let W1, W2, etc. Wm be the maximum linearly independent vectors in W. Maximum linearly independent vectors in W. Then what will happen? M will be maximum, m takes the value, maximum it to be n. So m is always less than or equal to n. Okay, we show these vectors, m vectors W1, W2, etc. Wm forms a basis of the subspace W, so that dimension of W is equal to m, which is less than or equal to n, which is the dimension of n. Okay, so to show this forms a basis of W, say first I will show these are linearly independent, and also they span W. Okay, they span W as well as they are linearly independent. For this, let W belongs to W be any element. If W belongs to W is any element, then the set W, W1, W2, etc. Wm is linearly dependent. Why? Because we have assumed that m is the maximum number of linearly independent vectors in W. Therefore, if I add one element, it becomes m plus 1, which is certainly linearly dependent set. If this is linearly dependent set, means what will happen? There exists a corresponding scalars alpha, alpha 1, etc. alpha m. Not all of which are zeros, means some of them may be 0, such that the linear combination alpha into W plus alpha 1 into W1, etc. alpha m into Wm is equal to 0. You call this by number 1. Now, if I assume alpha is 0, alpha is 0 means in the expression, if alpha is 0, what will happen? Alpha 1 into W1, alpha 2 into W2, etc. alpha m into Wm is equal to 0. If this is equal to 0, since W1, W2, etc. Wm are linearly independent, it implies that alpha is 0 for each I. Now alpha is 0 and each alpha is 0 means this set W, W1, W2, etc. Wm becomes linearly independent. But this is a contradiction, because we have assumed that m is the maximum number of linearly independent vectors in W. Okay, therefore alpha cannot be 0. If alpha cannot be 0, then since alpha lies in a field F, alpha inverse exists. Then multiplying throughout by, or from equation 1 we will have alpha can be written as, from equation 1 alpha can be written as, then from equation 1 W can be written as, you transfer alpha s all the terms onto the right hand side and multiply throughout by alpha inverse. You get minus alpha inverse into alpha 1 into W1 minus alpha inverse into alpha 2 into W2, etc. minus alpha inverse into alpha m into Wm. Now these are again the scalars. Alpha, if alpha belongs to W, alpha inverse also belongs to W, minus alpha inverse into minus alpha inverse is also belongs to W into L1 is also element of, these are elements of F. If alpha belongs to F, alpha inverse belongs to F, minus alpha inverse belongs to F, minus alpha inverse into alpha 1 belongs to F. Likewise, all these are elements of F. So therefore, W being written as a linear combination of scalars W1, linear combination of scalars using the vectors W1, W2, etc. Wm. Means W we have taken to be any element of W that being written as a linear combination of these m elements. Therefore, what you can say? Okay, W1, W2, etc. Wm. Therefore, W1, W2, etc. Wm forms a basis of W1, W2, etc. Wm forms a basis of W. Forms a basis of W. Consequently, since they already we assume that this is a linearly independent set, therefore they forms a basis. Therefore, dimension of W is equal to m. But m is we have assumed to be less than or equal to n, which is the dimension of V. Therefore, dimension of W is less than or equal to dimension of V. Okay, one part we have proved. Let's come to the second part. The second part is dimension of V by W is equal to dimension of V minus dimension of W. Okay, so now we have taken, let dimension of W is equal to m. and let W1, W2, etc. Wm be the basis of W. Then W1, W2, etc. Wm are linearly independent in W, and so they are linearly independent in V. And so now they are linearly independent in V, then these linearly independent vectors can be extended to form a basis of V. Okay, I will extend these elements to the set containing W1, W2, etc. Wm. I add the other R number of elements V1, V2, etc. Vr. W1, W2, etc. Wm, V1, V2, etc. Vr be the extended basis of V. Be the extended basis of V. Then dimension of V is equal to what? M plus R number of X elements. Dimension of V is equal to M plus R. Now you consider the set S. You consider the set S containing the elements W plus V1, W plus V2, etc. W plus Vr. You consider elements set containing W plus V1, W plus V2, etc. W plus Vr. Definitely these are all elements belongs to V by W. You know that V by W contains set of all elements of the form W plus X, where X belongs to V. Now V1, V2, etc. V are elements of V, therefore W plus V1, W plus V2, etc. W plus Vr are the elements of V by W. I will denote this set by S. Now we show that S forms a basis of V by W. So first let us show that S is linearly independent. So S is linearly independent means you take the linear combination of the elements of S. So alpha 1 into W plus V1, alpha 2 into W plus V2, etc. alpha R into W plus Vr is equal to 0. 0 means what? What is the element? 0 element of V by W? It is W. So 0 means W I taken. So by using the property of a cosets, this can be written as W plus alpha 1 V1, second element is W plus alpha 2 V2, etc. W plus alpha R Vr is equal to W. So this implies W plus alpha 1 V1, alpha 2 V2, etc. alpha R Vr is equal to W. Now W plus some X is equal to W means X belongs to W. Accordingly, alpha 1 V1 plus alpha 2 V2, etc. alpha R Vr is an element of W. But W has a basis elements. What are the basis elements of W? W1, W2, etc. Wm are the basis elements of W. Therefore, this element alpha 1 V1 plus alpha 2 V2, etc. alpha R Vr can be written as a linear combination of W1, W2, etc. Wm. Therefore, we return we return that element, say alpha 1 V1, alpha 2 V2, etc. alpha R Vr as linear combination, say beta 1 W1, beta 2 W2, etc. beta m Wm. This implies alpha 1 V1 plus alpha 2 V2, etc. alpha R Vr, you transform the terms onto the left hand side, minus beta 1 W minus beta 2 W, etc. minus beta m Wm is equal to 0. This implies what? This implies since this is equal to, since V1, V2, etc. Vr, W1, W2, etc. Wm are linearly are the basis of V, therefore each alpha is equal to 0, beta j is equal to 0, where alpha takes the value from 1 to R, I takes the value from 1 to R, j takes the value from 1 to m. Okay, therefore we can consider that in particular, each alpha I, beta j are 0 means I will take particularly alpha i's are zeros. If alpha i's are zeros means the linear combination which we have taken, say alpha 1 W1, alpha 1 into W plus V1, alpha 2 into W plus V2, etc. alpha R into W plus Vr is equal to 0, and each of the alpha i's are 0 means this set S forms linearly independent. This set S is linearly independent. Next, we show this set S spans V by W, that is L of S is equal to V by W. So for this what we will take? We will take the general element W plus X be any element of V by W. Then W plus X is any element of V by W means X belongs to V, and therefore X can be written as a linear combination of basis elements of V. Therefore X can be written as alpha 1 V1, alpha 2 V2, etc. alpha r Vr plus beta 1 W1, beta 2 W2, etc. beta m Wm. So this is equal to, now beta 1 W1, beta 2 W, etc. beta m Wm is an element of W. Therefore this element plus W is equal to W itself. Therefore W plus alpha 1 V1 plus alpha 2 V2, etc. alpha r Vr. So this can be written as W plus alpha 1 V1 plus W plus alpha 2 V2, etc. W plus alpha r Vr. So this is equal to alpha 1 times W plus V1, alpha 2 times W plus V2, etc. alpha r times W plus Vr. Thus, the arbitrary element W plus X in V by W is being written as a linear combination of elements of S. Therefore, S spans V by W. S is already linearly independent. Now we have shown S spans V by W. Therefore, S is a basis for V by W. S is a basis for V by W means, therefore dimension of V by W is equal to R, because S contains R number of elements. R is what? R can be written as R plus M minus M. R plus M is dimension of V, M is dimension of W. Therefore dimension of V by W is equal to dimension of V minus dimension of W. Okay, dimension of V minus dimension of W. Thus, we have shown that if V is finite dimensional, then V by W is also finite dimensional. If V is finite dimensional, V by W is also finite dimensional. Now, can the converse of this result holds true? Okay, the answer is no. The converse may not hold true. Okay, for example, you consider V to be the set of all polynomials in X. V to be the set of all polynomials in X over the field F. So V is equal to F of X, and let W be the subspace of V such that W is equal to set of all X square into F of X, where F of X is a polynomial belongs to V. W is equal to set of all X square into F of X belongs to V. Now means what will happen? The polynomials in W definitely are minimum are polynomials of degree 2 only, because every element is multiplied through X square. Okay, then W is a subspace of V, and V by W is what? That's good. V by W is equal to set of all X plus X plus W, where X belongs to V, right? So that is the standard definition. So this is equal to, since W is set of all X square into F of X, V by W is equal to, the element missing in V by W are W plus A0 plus A1x, because A0 plus A1x cannot lies in W. So W plus A0 plus A1x, where A0 and A1 belongs to F. Clearly V by W is spanned by which one? Clearly V by W is spanned by W plus 1, because I need A0 means constant term, W plus 1 and W plus X. So V by W is spanned by W plus 1 and W plus X, and so V by W is finite dimensional. V by W is spanned by only these two elements, therefore dimension of V by W is 2, and so V by W is finite dimensional, but V is not finite dimensional. V is not finite dimensional because what is the dimension of F of X? We don't know what is the degree of a polynomial in F of X here, V. So it may be infinite dimensional 1, it's a polynomial like A0 plus A1x, A2x square and so on. Okay, so means the basis elements are 1, x square and so on. So though it's an infinite dimensional, the dimension of the quotient space V by W is finite dimensional. Next, let us take up another result. So this result says if W1 and W2 are subspaces of a finite dimensional vector space V, then dimension of W1 plus W2 is equal to dimension of W1 plus dimension of W2 minus dimension of W1 intersection W2. So dimension of W1 plus W2 is dimension of W1 plus dimension of W2 minus dimension of W1 intersection W2. Now we already proved in the last class that If W1 and W2 are subspaces of a vector space V, then W1 plus W2 by W1 is isomorphic to W2 by W1 intersection W2, where we have taken, instead of W1 and W2, we have taken A and B, that's all. Okay, this implies these two subspaces are isomorphic, means their dimension must be the same, because we have proved one result in the last class itself. Any two finite dimensional vector spaces are isomorphic if and only if they have same dimension. Accordingly, dimension of the left hand side W1 plus W2 by W1 is equal to dimension of W2 by W1 intersection W2. Now what will happen? According to the above theorem, dimension of V by W is equal to dimension of V minus dimension of W. Accordingly, this dimension of W1 plus W2 minus dimension of W1 on the left, and dimension of W2 minus dimension of W1 intersection W2 on the right. This implies dimension of W1 plus W2 is equal to, you transform this term to right hand side, this is equal to dimension of W1 plus dimension of W2 minus dimension of W1 intersection W2. Okay. Now suppose dimension of W1 intersection W2 is 0. 0 means they both are W1 and W2 are zeros. Okay, they are not equal. W1 and W2 are not equal, because 0 definitely common in any subspace, because if you want to be any subset to be a subspace, 0 is always present in there. Suppose W1 intersection W2 is equal to 0, then what will happen? Then the direct sum of dimension of the direct sum W1 plus W2 is equal to dimension of W1 plus dimension of W2. Already we have proved this result. Okay, so this is using the above theorem. Dimension of the dimension of the direct sum of the subspaces W1 plus W2 is equal to dimension of W1 plus dimension of W2. Okay, and also we can prove this result, which we already proved in the last class itself. So again I am going to prove it now. Let W be a subspace of a finite dimensional vector space V. Let W be a subspace of a finite dimensional vector space V. Then there exists a subspace, another subspace W dash of V, such that V is the direct sum of W plus W dash. V is the direct sum of W plus W dash, direct sum. Okay, for this, now W is a subspace of a finite dimensional vector space V, means W is also finite dimensional. Already we have proved. Okay, subspace of a finite dimensional vector space V is also of finite dimensional. So it is finite dimensional, means it has a finite number of basis elements. Okay, for that let W1, W2, etc. Wm be a basis of W, a basis of the subspace W. Now W1, W2, etc. Wm is a basis of W, means they are linearly independent in W. If they are linearly independent in W, certainly they are linearly independent in V also. So W1, W2, etc. Wm are linearly independent in V. If they are linearly independent in V, then you know that this set can be extended to form a basis of V. Okay, I will extend the above set to form a basis of V as I add W1, W2, etc. Wm, V1, V2, etc. Vr be a basis of V. I add the elements V1, V2, etc. Vr be a basis of V. How to choose V1, V2, etc. Vr is, you know that. So we choose V1 so that V1 does not lies in the span of W1, W2, etc. Wm, and we add this element V1. Next we take another element, say V2, and we will see that whether V2 belongs to the linear combination of these elements. If that doesn't belong to the linear combination, then we add V2. Likewise, we add the elements or number of elements, so that will be the maximum number of linearly independent vectors. Okay, so we have taken W1, W2, etc. Wm, V1, V2, etc. Vr to be basis elements of V. Now let W dash be the subspace of V spanned by V1, V2, etc. Vr, or number of basis elements. Okay, let W dash be the subspace of V spanned by the second set of vectors V1, V2, etc. Vr. Then what will happen? any element, any vector v belongs to v can be written as v is equal to, so these are the basis, total m plus r number of basis elements. Therefore, any element v belongs to v can be written as v is equal to alpha 1 w1, alpha 2 w2, etc. alpha m wm plus, I group this first term, plus beta 1 v1, beta 2 v2, etc. beta r vr. Okay, first set is an element of, definitely these are the basis elements, means the linear combination of basis elements belongs to W, and the second is the linear combination of these elements of W dash. Therefore, the elements in the second bracket belongs to W dash. Therefore, this total element V belongs to W plus W dash. So, we have taken the element V belongs to V and we have shown that that element belongs to W plus W dash. Therefore, V is contained in W plus W dash. But already clearly W plus W dash is contained in V, because W is also a subspace of V, W dash is also a subspace of V. Therefore, sum of any two subspaces is again a subspace of V. Now, we can conclude that V is equal to W plus W dash. Okay, V is the sum of W as well as W dash. Okay, next let us show that what will be the element we present in the intersection. Let x belongs to W intersection W dash. This implies what? X belongs to W as well as x belongs to W dash. Now, if x belongs to W means x can be written as a linear combination of basis elements of W. Therefore, x can be written as alpha 1 W1, alpha 2 W2, etc. alpha m Wm is one possibility. The other possibility is x belongs to W dash means x can be written as beta 1 V1, beta 2 V2, etc. beta r Vr is the other possibility. Therefore, x can be written in two ways, but this cannot be possible. Therefore, this must be equal to alpha 1 W1, etc. alpha m Wm is equal to beta 1 V1, etc. beta r Vr. This implies what? Alpha 1 W1, etc. alpha m Wm, you take the right hand side terms to left hand side. So, this becomes minus beta 1 minus beta 2, etc. minus beta r Vr is equal to 0. Now, we can see that this is a linear combination of Wi's and Vi's. Therefore, since these W1, W2, etc. Wm, V1, V2, etc. Vr forms a basis of V, therefore, this each alphas must be 0 because they are linearly independent. All these vectors W1, W2, etc. Wm, V1, V2, etc. V are all linearly independent. Therefore, each alpha is must be 0. I takes the value from 1 to m, and each beta j must be 0, where j takes the value from 1 to r. Therefore, each of the alpha is and beta j's are 0 means what you can write? We can write that, we can say that the x itself is 0 because all the elements are 0. Therefore, x is equal to 0. The element x we have taken in the intersection and we have shown that that x itself is 0 means all the elements in W intersection W dash is equal to 0 because x is an arbitrary element we have taken in W1 in W intersection W dash, and we have shown that that is x itself is 0 means W intersection W dash is equal to 0. Already we have shown V is the sum of W plus W dash, and we have shown W intersection W dash is equal to 0. Therefore, by definition of the direct sum, we can conclude that V is the direct sum of W1 plus W2. V is the direct sum of W1 and W2. Okay. Next, let us take up another concept. Suppose V and W are any two vector spaces over a field F. Suppose V and W are any two vector spaces over a field F. Then you know that the homomorphism can be defined from V to W. A homomorphism from V to W is a mapping T from V to W such that T of alpha x plus beta y is equal to alpha into T of x plus beta into T of y. This holds for every xy belongs to V and alpha comma beta belongs to F. Okay. Now, T is a homomorphism from V to W. Okay, you know that as many as number of homomorphism can be defined from V to W. Then totally how many homomorphisms can be defined from V to W? Let us discuss in this class. Okay, so I will denote all the homomorphisms from V to W, all the homomorphisms from V to W by the set Om of VW. Om of VW denotes set of all mapping T such that set of all mapping T from V to W such that T is a homomorphism. T is a homomorphism. Om of VW contains set of all homomorphism from V into W. So now we will show that this Om of VW itself is a vector space. How do you define the operations? Say you take any two elements T1 comma T2 be to any two elements of Om of VW. You take T1 comma T2 be any two elements of Om of VW. Say alpha is a scalar. Then we define the sum of these T1 plus T2 of x is equal to T1 of x plus T2 of x. Now T1 of x is an element of where? W. T2 of x is an element of W. Therefore T1 of x plus T2 of x is an element of W because W is a subspace. Therefore T1 plus T2 of x is an element of W. Therefore the mapping is well defined. Similarly alpha into T1 of x. Similarly alpha into T1 of x I will define to be alpha times T1 of x. Now T1 of x is an element of W. Alpha into any element of W is again in W. Therefore alpha into T1, the mapping alpha into T1 belongs to Om of VW. Therefore T1 plus T2 belongs to Om of VW and alpha into T1 also belongs to Om of VW. Okay, so Om of VW is closed under vector addition and scalar multiplication. Okay, we can prove the other properties of a vector space. We can prove the other properties of a vector space that holds in Om of VW. Okay, says here 0 is the 0 of x is equal to 0 for every x belongs to V is the 0 element. Okay, and the additive inverse of T1 is minus T1. Additive inverse of T1 is minus T1. Okay, so Om of VW forms a vector space under the above two operations. The important question is here, what will be the dimension of Om of it? It is a vector space. Okay, then what will be its dimension? Okay, that's an important part of this class. Say suppose dimension of V is n. Dimension of V is n and dimension of W is m. If dimension of V is n and dimension of W is m, okay, then dimension of Om of VW is m into n. Dimension of Om of VW is m into n means there are m into n number of basis elements for the vector space Om of VW. That we are going to show in this class. Okay. So for this, since dimension of V is n, there are n number of basis elements, and dimension of W is m means there are m number of basis elements for W. So let V1, V2, etc. Vn be a basis of V and W1, W2, etc. Wm be a basis of W. Okay. Now define the transformation, set of transformations or set of homomorphism Tij from V to W given by, because I takes the value from 1 to n, j takes the value from 1 to m. Therefore, how many Tij's are there? There are m into n possibilities, because I takes the value 1. 1 means T11, T12, T1, last is m, T1m, m number. Next T21, T22, T2m. Next likewise Tn1, Tn2, Tnm. Therefore, n number of homomorphisms we define from V to W. They are given by Tij of any element vector Vk. Tij of Vk is Wj. This is very important. Tij of Vk is Wj if I is equal to k and 0 if I is not equal to k. Tij of Vk is Wj if I is equal to k and 0 I is not equal to k. Now I can be any of 1 to n and j can be any of 1 to m. Therefore there are m into n such Tijs. So I'll collect these Tijs in the set S. Say let S be the set containing these homomorphism Tijs T11, T12, etc. T1m. Next T21, T22, etc. T2m, etc. Tn1, Tn2, etc. Tnm. N into m number I collect. Okay. We show that this set S forms a basis of O mod VW, so that dimension of O of VW is n into m. Okay. Before that, so we need to show the above mapping Tij which define from V to W whether it is a homomorphism or not, because if it is a homomorphism then only it will be in the basis set. Okay, whether Tij belongs to S or Tij belongs to home of VW or not. Let us check. Okay, for this what we have to do? So we have to check the linearity condition, that means homomorphism condition. For this we will take x and y belongs to V be any elements and alpha comma beta be scalars. Then x comma y belongs to V means how x looks. X is the linear combination of v1, v2, etc. vn, that is alpha 1 v1, alpha 2 v2, etc. alpha n vn, and y will look like beta 1 v1, beta 2 v2, etc. beta n vn. Therefore Tij of x is according to our convention what will happen? Tij of x is Tij of alpha 1 v1, Tj of alpha 2 v2, etc. Tij of alpha n vn. Okay, understand now? So this is equal to what? Alpha 1 into Tij of v1 plus alpha 2 into Tij of v2 and so on, alpha n into Tij of vn. So this becomes Tij of x is equal to all other elements becomes 0 only when I is equal to k, it takes the value Wj. Therefore Tij of x is equal to what? Alpha into Wj remains. Tij of x is alpha into Wj, and Tij of y is what? Beta I into Wj. Tij of x is alpha I Wj, Tij of y is beta I Wj. Now x plus y is what? Alpha 1 plus beta 1 into v1, alpha 2 plus beta 2 into v2, etc. alpha n plus beta n into vn. Therefore I will consider Tij of alpha x plus beta y. Now Tij of alpha x plus beta y means you may consider alpha x plus beta y here and you apply Tij, that you can see, that you can observe to be alpha into alpha I plus beta into beta j into Wj. So this is equal to alpha into alpha I Wj, I will combine, plus beta into, so this is beta into beta I, so this is beta I Wj. The alpha into alpha I into Wj plus beta into beta I Wj. So this is equal to alpha into Tij of x plus beta into Tij of y. Therefore Tij is linear, means therefore Tij is a homomorphism, and so Tij belongs to home of VW. So Tij is an element of home of VW. Now let's come to showing that Ts is a basis for home of VW. So first we show S spans home of VW. S spans home of VW means I will take arbitrary element of home of VW and I will show that arbitrary element is a linear combination of the elements of S. Okay. So for this, let T belongs to home of VW be arbitrary. Okay. And V is equal to alpha 1 V1 plus alpha 2 V2 etc. alpha n Vn be any element of V. Okay, T is an element of home of VW and V is an element of V. Then T of x is what? T of V is alpha 1 into T of V1 plus alpha 2 into T of V2 etc. alpha n into T of Vn. You call this as number 1. Now T of V1 where it lies? If V1 belongs to V, T of V1 belongs to W, T of V2 belongs to W, etc. T of Vn belongs to W. So these n elements, T of V1, T of V2, etc. T of Vn are elements of W, but W as a basis. W1, W2, etc. WMR is a basis of W. Therefore, these n vectors can be written as a linear combination of elements, basis elements of W. Okay. Therefore, I written, say, these elements T of V1, these elements T of V1, T of V2, etc. T of Vn as basis elements of W. Okay. So, T of V1 is equal to, I will index this as lambda 11 W1 plus lambda 12 W2, etc. lambda 1m Wm. Similarly, T of V2 is what? Lambda 21 W1, lambda 22 W2, etc. lambda 2m Wm. Likewise, the nth element T of Vn can be written as lambda n1 V1, sorry, lambda n1 W1, lambda n2 W2, etc. lambda nm Wm. You call this as number 2. You substitute all these values T of V1, T of V2, etc. T of Vn in 1. Then what you get? T of V is equal to alpha 1 times T of Vn means, T of V1 means you write lambda 11 W1, lambda 12 W2, etc. lambda 1m Wm. Next, alpha 2 into T of V2 is, you write like this. Similarly, plus alpha n into T of Vn can be written as lambda n1 W1, lambda n2 W2, etc. lambda nm Wm. Okay. So now this is equal to, I'll write like this, lambda, because these are scalars, alpha beta V is what? Alpha times into beta V or beta times into alpha V. So accordingly, this is equal to, I'll take lambda 11, because look here, alpha 1 and lambda 11 are scalars, means they are in the field F. Means field F means field is it is abelian group under multiplication also. Therefore, alpha into beta is same as beta into alpha in F. Okay. So this is equal to lambda 11 into alpha 1 W1 plus lambda 12 into alpha 2 W2 and so on. Lambda 1m into alpha 1 Wm is the first row. So likewise, the last element is lambda n1 into what? Alpha n W1, lambda n2 into alpha n W2, etc. lambda nm into alpha n Wm. So this is equal to lambda 11 into alpha 1 W1 can be written as what? T, by definition of Ti is T11 of V plus lambda 12 into T12 of V, etc. lambda 1m into T1m of V. Likewise, lambda n1 into, this is Tn1 of V, lambda n2 into Tn2 of V, etc. lambda nm into Tnm of V. Thus, the element T of V belongs to W can be written as the n into m number of elements which are in S. Therefore, what you can say? So S spans, therefore S spans ohm of VW. That means it holds for every V means, so this is can be written, T can be written like this. So S spans ohm of VW. Now the other thing is S is linearly independent. So you consider the linear combination lambda 11 T11 plus lambda 12 T12, etc. lambda 1m T1m and so on. Last element is lambda n1 Tn1, lambda n2 Tn2, etc. lambda nm Tnm is equal to 0 you consider. Means the linear combination of elements of S is equal to 0. Now what we have to show? Each of the scalar coefficients will be equal to 0. So this implies lambda 11 into T11, lambda 12 into T12, etc. above expression over Vk. These are all the set of transformations. So this is of Vk is equal to 0. Of Vk. This is equal to right hand side 0 means 0 of Vk. 0 is a 0 transformation. 0 of Vk is what? 0 itself. So now what will happen? Lambda 11 into T11 of lambda 11 into T11 of Vk. Here what will happen? By definition of Ti is by definition of Ti's, what will happen? Tij of Vk is Wj if I is equal to k and 0 elsewhere. 0 when I is not equal to k. According to that, what will happen? So every element, every T11 of Vk, everything gets zeros. Only lambda k1 into Tk1 of Vk. Tk1 of Vk becomes W1 plus lambda k2 into W2 etc. Lambda kj into Wj and so on. Lambda nm into Wm. Lambda nm into Wm is equal to 0. Lambda k1 W1, lambda k2 W2, lambda kj Wj etc. Lambda k. So this must be lambda km into Wm must be equal to 0. So now W1, W2 etc. Wm are linearly independent, means each of the scalar coefficients must be 0. This implies lambda kj is equal to 0. Now if we act on Vk, the above expression acting on Vk gives lambda kj is equal to 0 for every k lies between 1 to n and for every m lies between for every j lies between 1 to m. Therefore this expression over V1, this expression over V1 gives what? Lambda 11, lambda 12 etc. lambda 1 m is equal to 0. This expression over V2 gives lambda 21, lambda 22 etc. lambda 2 m is equal to 0. Likewise this expression over Vn gives lambda n1, lambda n2, lambda nm. They are all zeros, means each of this linear combination will be equal to 0. Means what will happen? So these scalar coefficients will be equal to 0. So if you assume that a linear combination is 0 and each of the scalar coefficient is 0, means what you can say? S is linearly independent. Okay, we have taken over the arbitrary vector Vk. Likewise V, it is over this over V arbic, this over V should be. V means V is a linear combination of basis elements, that is V1, V2 etc. Vn. Okay, so we can observe that each of the scalar coefficients lambda ij's are zeros. Therefore we can declare that S is linearly independent. Already S is spanning Ohm of Vw. Now S is linearly independent, means S forms a basis of Ohm of Vw. But how many elements are there in S? There are n into m number of basis elements. Therefore dimension of Ohm of Vw is n into m. That is okay, that is the dimension of V, that is the dimension of W. Okay, now if dimension W is equal to V, what will happen? If W is equal to V, that means dimension of Ohm of Vv is n into n, it becomes n square. Okay, dimension of Ohm of V means what? Set of all homomorphism from T from V to V. That's such type of homomorphisms are called linear operators, that we will discuss in the linear transformation. Those are called linear operators. And if we take instead of W, if we take F, then what will happen? Dimension of Ohm of Vf is what? N, because n into 1. N into 1 is n, because the dimension of the vector space F over F itself is 1. You know that. If in the beginning itself we have shown, if F is a subfield of a field K, then dimension of the vector space K over F is, then K over F can be treated as a vector space. Okay, therefore F over F is a vector space and the dimension of the vector space F over F itself is 1. Okay, so if the dimension of the vector space Ohm of Vf is n. Okay, so this is the one of the important result in this class. Okay, thank you.